This is video number 6. This is Introduction to Hypothesis Testing, which is test 4 material. So we've come off of confidence intervals, which is a way for us to have a range of possible values for either the population mean or the population proportion. And confidence intervals are a wonderful thing. Hypothesis tests are more powerful. They are going to ask a specific question. Quick little example might be when you flip a coin. You're probably going to assume that your coin is a fair coin, meaning the probability of heads is 0.5. Let's say you flip it 100 times. We have talked about this probably a month ago. But if you came up with just 40 heads or 60 heads, you would probably assume that's just random variability. We know we're not expecting exactly 50 heads because that's that long-term probability. But what if when you flipped a coin 100 times, you actually got 90 heads, period? That would be a bit unusual. You're going to think one of two things. You're first probably going to think, I guess my coin is not fair. You can go to magic shops and buy unfair coins. They're weighted a little bit different to kind of trick you. So if you ended up with 90 out of 100 heads, you would probably think, yeah, I think I have a screwed up coin. Meaning you would think the initial assumption of a fair coin, 50% heads, is wrong, that you have an unfair coin. And that's probably would be a pretty good assumption. Towards the end of this video, we're going to talk about some mistakes or errors you can make. Actually, maybe you just had an extremely unusual thing happened to you when you flipped 90 heads. Maybe it really is a fair coin, and the probability of you flipping 90 heads is probably beyond tiny, like a hair above 0, but it's still technically possible. The probability is not 0%, so maybe you had that 1 in, 20 million chance thing happen to you. That's what hypothesis testing is about. That when we actually see what we see in real life, if the probability of that was so small, we start to think our initial assumption was wrong. But there is always that chance that it was an appropriate result. It was just an unusual result. So we could be making a mistake also. That's sort of an introduction. Let me couch it another way. I always tell you guys, I don't think you're going to win the big lottery. The chance is like 1 in 300 million or something. I'm really passionate. I don't think you're going to ever win the big lottery. But let's say you go buy a ticket and you come back in a couple weeks and you tell me, I won the lottery, Miss Watson. You know, at first I'm not going to believe you. I'm probably going to make you tell me 10 times and show me the ticket. I am basing my passion on that I know the probability is so tiny. But then when you show me the ticket and I verify that you actually won, I'm going to have to sit there and say, wow, I was wrong. The probability was so tiny that I really did not think you were going to win the lottery, but it wasn't 0% since you bought a ticket. And since you won, I have made a mistake. I've made an error. So again, in all hypothesis testing, of course, there's always that small chance we're going to make a mistake. If you want to save yourself writing, again, you can print out the notes. I'm going to write the notes on the board in case you don't have access to a printer. I'm going to write and then I'll read it to you. These, for those who printed, these are the notes I'm on. Someone claims there is 60% females at JMU. I get there and I take a sample and I find 95% are actually female. How likely is it that if there really was 60%, that I would actually find a sample with 95%? If this is a tiny probability, I start to think the original 60% is false. So this is just a little more formal of the example that I introduced you verbally to a few minutes ago. This idea of calculating the probability to see if it's tiny or not, that is sampling distributions, handout 9. So again, that is why we study sampling distributions, the topic that you don't necessarily love from test 3. This was, so that's a long example, right? This was a quick little definition, an introduction to hypothesis testing I stole from a different textbook. An outcome that would rarely happen if a claim were true is good evidence the claim is not true. So that's just a little more formal way of saying it. I'm going to erase. You can pause if you need to continue writing. Let's get some of the language or notation that we're going to be using. HO or H naught is the null hypothesis. This is the claim about the population initially assumed to be true. For example, so by the time we finish test 4 material, we're going to have done 4 different hypothesis tests, but our 2 basic ones is going to be for population mean, mu, or population proportion, p. So for example, we might have mu equals 1,000, or you might have maybe the population proportion is 0.4. You wouldn't have both of those, just one or the other. Someone else comes along and says, hold on, I don't think you're right. This is what I think. That is called HA for the alternative hypothesis. Just to let you know, old school notation and possibly in science class, they might use a 1 there. It doesn't matter. The A is the more popular notation lately. The alternative hypothesis. This is the competing claim. So for example, someone says, yeah, I don't think mu is 1,000. They might say, I think mu is less than 1,000. Or they might say, I think mu is greater than 1,000. Or they might say just simply, I don't think it's 1,000. So there's, right now I'm already showing you, there's only 3 notations you're ever allowed to have in HA. Also, I can tell you right now, HO is always going to be the equal sign. Probably in class or the next video, we're going to learn that if you're strictly going greater than or less than, it's called a one-sided hypothesis test. When you're doing a not equal, it's called a two-sided. That stuff will become more important as we go through test 4 material. And then, of course, you're going to use sample data to decide between the 2. Maybe, again, just to give you an idea of where we're going in this video, it's all going to be background. There's going to be some really important rules that we learn. Trying to explain graphically what this stuff means. In just a few minutes, we're actually going to compare it to the crime court justice system in America. Sounds silly, but it really helps students understand why we have to be extremely careful and picky on the way we word our final conclusions and our interpretations. I'm going to erase. let me come at something graphically first, just to try to give you the big idea of what we're doing. I'm attempting, well, of course on this video I can use different colors. On my notes I tried to just use dotted lines since it's all black and white. Let's just say, for example, we're trying to figure out if the population mean is 7 or if it's greater than 7. So this first curve is representing my mu equals 7, something unimodal and symmetric around 7. This curve, we'll call this curve number 1 and this curve number 2 just so we can stay organized. This curve is representing something bigger than 7. I don't know if we're talking 8 or 7.6 or 9, just something bigger than 7. Now, it's all about taking samples, right? So let's say we take a sample and he lands way out here. See how I put him in the tail of the HO number 1 curve. You already kind of know what this means. Just from test 2 and test 3 material, maybe that was a z-score of like 3.5 or 3.7 or something, right? We'll call him sample A. Now, let me get my green. Let's say we don't take 2 samples at once. I'm just trying to compare and contrast. Let's say we got a sample and he landed right here. I don't know, maybe this would have been a z-score of 0.7 or a z-score of 1 or something. Not that far out, kind of still in the middle. We'll call him sample B, as in boy. Just the big idea right now. Sample A. See how he's way out in the tail? So this is when, particularly when we're in the classroom, I get very cute with my language because I don't want to scare people with formal statistical theory. You're going to hear me for the next month talk about this being a mountain, and these 2 ends, they are called tails, but I'll start calling them cliffs as if you're about to fall off the cliff to your death from some mountain that you're on. So see sample A? See, sample A is getting so far out in that tail, or a little more cutely, he's about to fall off the ledge. Let's just keep talking about my red sample A. I can say it in a lot of different ways. He is so far out in that tail of curve number 1, right? While I'm taking a little bit of freedom here with what's in parentheses, if you visualize it, yeah, he seems to fit curve number 2 better. True hypothesis testing does not test how well it fits curve 2. It only tests does it fit curve 1 or not, but I'm just trying to give you the big idea right now that I feel like sample A is about to fall off my mountain being curve number 1. So I don't think you're part of my mountain anymore. I don't think this sample came from curve number 1. So thus, the language we're going to learn that we're going to use is reject HO. I'm rejecting this mountain. I don't think sample A came from here because you're so far out in that tail. Basically, the probability would be so tiny. I'm going to erase and then we're going to talk about sample B, the green one. So sample B. Granted, he's not directly in the middle of the mountain. We don't expect him to be, right? We always know there's random variability. So that's why I'm using quotes around sample B fits curve number 1 just fine. We all know what the word fine means, right? It's not perfect, but it's just fine. You can tell my sample B, the green line, does not look like it's going to fall off my mountain. I'm not worried about him like I am about sample A. When it seems to fit just fine, the language we're going to use is do not reject HO. Do not reject the null hypothesis. You'll hear me say this many times, but I'll start right now. We are never, ever, ever gonna say accept HO. It's all a matter of either rejecting HO or do not reject HO. The next time we come back to this topic, we're going to go through the 5 steps of hypothesis testing, and you're going to see the language on step 5 clearly tells you you're only allowed to say one of 2 things. Either what we said about sample A, reject HO, or what we said about sample B, do not reject HO. You are never ever using that language. While at this point it might seem a little semantics, like I'm being real picky on words and it really doesn't matter. That is why I'm about to erase. I want to present it to you from the American court system. A lot of books are doing this now also. Let me erase. I'm going to split my screen here. Okay, so up until today, what we've done for statistics is we've done confidence intervals, right? Let's say, for example, we calculated a confidence interval for mu, and we knew it was somewhere between 10 and 20. That totally relates to when a crime has been committed. We all get the different alerts from JMU, and normally they don't know exactly who did it. They just give us a brief description, maybe something like this. They might say we're supposed to keep our eye out for a tall white male. Now, both of these have reduced the population down, right? I mean, sure, it can't be 50 or 0, somewhere between 10 and 20, but there's still a lot of numbers between 10 and 20. The same thing here. This has reduced the human population down, but there's still a whole lot of tall white males. So these are very synonymous. Now, let's say they go arrest one particular tall white male and we're in court. Now the question is, we always name him John Doe. Did John Doe do it? So he's the defendant, he's sitting in court, and the question is, did that one particular tall white male named John Doe, did he do it? This is exactly what we do in hypothesis test. Instead of just saying, oh, it's somewhere between 10 and 20, we're actually going to ask a specific question. For example, we want to see, is mu 15 or not? We're asking a specific question on one of these specific numbers. Okay? When you're in the court system, I hope that everybody does understand this about the American court system. A little bit of evidence is not going to do it. You need a ton of evidence. Sometimes they call it a preponderance of evidence, evidence beyond a reasonable doubt. Basically, you need a ton of evidence. Same thing in statistics. I'm going to kind of just write that across both sides. You absolutely need evidence beyond reasonable doubt. You need a lot of evidence. All right, back to the American court system. What if there's not enough evidence? If you've watched any court, what do you call them, crime shows on television, hopefully you already know this. If there is not enough evidence, they do not proclaim John Doe innocent. What they proclaim is not guilty. They will never call him innocent. I mean, we hope he's innocent because we don't want a guilty man back on the streets, right? But that's not what they say. If there's not enough evidence, they will just proclaim John Doe not guilty. So if you buy into the difference between not guilty and innocent here, then you're going to understand the difference of why we have to say do not reject HO as opposed to saying accept HO. So if there's not enough evidence, we say do not reject HO. We never say accept HO. So hopefully understanding the difference in this language will help you understand why we have to be picky in statistics. I'm going to erase, but I have a few more on each side. Hopefully everybody knows this in the American court system, that we protect the defendant. What that means is the defendant does not have to prove his innocence. The prosecutor, the court, has to prove him guilty. We must prove him guilty with a ton of evidence, right? It's exactly what happens in statistics. We protect HO, the null hypothesis. John Doe gets to just sit there in court and technically he doesn't have to say a word. I mean, it's helpful if he does, but he doesn't have to. HO gets to sit there and does not have to prove a thing. The burden of proof is on HA. So HO does not have to prove itself true. We have to prove that HA is true. I'm looking on my notes. I want to make sure I put everything on the board that is on the notes. And one more time, if there's not enough evidence, we never say mu is 15. What we will say there's no evidence that mu is not 15. This is that wording that you guys don't like, but it relates to how we call John Doe not guilty. You're not going to say that HO is true, just like we're not calling John Doe innocent. Basically, in statistics, you're going to say there's not evidence of HA. And if you look back up, HA was mu not equal to 15. So you're going to say there's not evidence that mu is not 15. Again, we're going to be practicing this when we go through our 5 steps on lots of problems. Okay, I'm going to erase. We got a couple more graphical pictures. Everything's been very generic so far. Haven't figured out where the numbers are and the number crunching. Have a few more vocabulary words or whatever you want to call it. We only need one curve this time representing the null hypothesis. And we were talking about where our sample fell earlier. It doesn't really matter if it's A or B. Well, we'll go with, I don't want to confuse you, I think we had called that sample A. Okay? And visually we can see you're about to fall off my curve. But we're not going to have correct curves to scale so we can visually look at and say, oh yeah, I think you're about to fall off. Then what are we going to do? We are actually going to calculate probabilities, or at least our calculator is going to calculate probabilities. What I colored in was, so maybe I should write this. This is where my sample fell. The sample fell here, or the sample landed there. The formal word for that is the test statistic. Like, for example, maybe that one is a z-score of 3.8 or something. And you know, if it were a z-score of 3.8, you know how to calculate that probability. You would have to look up 3.8 on the z-chart, get the area, and then subtract it from 1 to get that area. So these things we already know how to calculate. Luckily, our calculator is going to do it all for us. But this area that I colored in is a really special area. It's called the p-value. We'll never just use plain p. We'll always say p-v-a-l-u-e. The p-value. The p-value is the tail probability, or area, right, past where your sample landed or where your sample fell. So you can kind of see how sample A has a very small p-value. Back to, I think I put sample B approximately right there. Look at the p-value for sample B. I'll do it in curly. He's pretty large, right? So sample A has tiny probability, tiny p-value. Thus, what did we say earlier? We were going to say reject HO. So when your p-value is tiny, that means you're about to fall off my mountain, which means I don't think you came from that curve, which means you're going to conclude reject HO. Now look at sample B. It has a pretty large p-value, which is going to relate to do not reject HO. Because if you have large p-value, it basically means you have fallen into the perfectly fine part of the curve. I'm not worried about you at all, which means do not reject HO. So I'm just trying to compare the p-value from sample A to sample B. I know I'm still being very vague, like how small is small enough to say reject HO, or how big is big enough where you're going to say do not reject HO. We are going to get to that. We're going to have very specific criteria. First, I need to put up a rule that you have to memorize whether you understand it or not. Then we'll take a couple minutes to see if we can get you to understand it. This is an alpha, not a 2. There are some students who memorize this incorrectly. It's used on every single problem on test 4 and half the problems on the final exam. If the p-value is less than or equal to alpha, you reject HO. We haven't even talked about alpha yet. So briefly, what is this alpha thing? Well, it represents a rejection region. Okay, my cat, come here. I thought my cat was going to walk in front of the board. Alpha, which is a rejection region, it is an error. Remember at the beginning of the video when I told you I did not think you were going to win the lottery? And I based that off of that it's such a tiny, tiny, tiny probability, but you end up coming in and showing me you did win, and I had to say, oops, I was wrong. That's what alpha is representing. Let me draw maybe a picture. Well, let me finish writing first. This really relates to confidence intervals. We don't like to be wrong that much in statistics. Alphas, our mistake, our error region is usually about 5% or 0.05 in decimals. This alpha in an interpretation sentence. 5% of the time we will see such an unusual sample that we will think it did not come from HO, but it really did. Next time either I make a video or I see you in the classroom, we're actually going to practice a lot more about the errors that can be made. But I just have one more graphic I want to show you to really try to get you to understand this, because our TI-83 is going to give us p-values. Those are just probabilities from sampling distribution. Alpha is going to be stated in the problem. So you're going to be comparing two numbers so you know which conclusion to make. This is all going to be very clear number crunching once we practice problems. I'm going to erase. One more picture. I'm trying to keep with the same mu equals 7, mu greater than 7. Everything I've been doing today has been up here. We could be down here also. It doesn't really matter. Okay, so alpha. Let's say, for example, it's the top 5%. That means that I know that if I find samples up there, I'm basically going to get tricked. It's going to make it look like you're about to fall off my ledge, fall off my mountain, and I'm going to say you didn't come from HO when you really did. You really were part of the curve. You're going to end up tricking me. That's why we called it a mistake, an error, because I got tricked. What has that got to do with my samples? Oops, I shouldn't have used red there. I'm going to go ahead and make this blue. Okay, that's the alpha region, that if you fall into it, we're going to think you didn't come from this curve. Remember sample A earlier? He was way out here. Well, just visually, you see how sample A has fallen into the rejection region? Maybe I should write that. Which means, yes, we're going to reject. What's that got to do with the p-value? Remember sample A? Sample A's p-value was tiny. See how the red p-value is smaller than the blue alpha? Remember this alpha, the rejection region, that I'm willing to be wrong 5% of the time? See how that p-value is smaller than the blue? That is why, for sample A, we decide we're going to reject HO, because the p-value is smaller than the alpha. Let's revisit sample B. Now, first of all, you can see that sample B did not fall into the rejection region. But again, we aren't going to have these pretty pictures when we're doing our problems. All we're going to have is p-values. The area, the probability, past where my sample fell, that's what a p-value is. So all of the green is the p-value. See how that is not less than or equal to the blue? It's bigger than the blue. The p-value is bigger than the alpha. The green p-value is bigger than the blue alpha. That is why for sample B, we're going to do not reject HO. So this hopefully shows you how we're going to get exact numbers. Our TI-83 is going to be calculating these probabilities for us, the green or the red. But actually, you already know how to calculate those probabilities because that's what we did with sampling distributions. We're just going to cheat and use shortcuts on our calculator from here on out. So this is just introduction background. Anything I've said in this video holds for any hypothesis test we're going to do, and we're going to end up doing 4 different hypothesis tests before we have test 4. But the next time I lecture to you, we're going to get more into the specifics and learn how to actually do, specific problems. All right. See you soon.